This is the lecture part for waves and sound. So in this chapter, for chapter 16, we're going to distinguish between transverse and longitudinal waves, calculate the speed, frequency, and wavelength of a wave, calculate the intensity of a sound wave, and solve problems using the Doppler effect. So the first thing that I recommend you do is go ahead and go to the Waves Intro FET. This is a simulation. You can just Google Wave Intro FET and you'll get there, or you can click on the link in the PowerPoint. Um, and the first thing I want you to look at is a pulse. So a pulse is one little boop. It kind of is one little piece of a wave. You might think of it as one wave, but really it's this thing is called a pulse. And you can look at it from the top down. Either way, it's one little bloop. And then a wave is a whole bunch of pulses all put together, repeating. And that's what a wave is. When we talk about sound waves are in reality actually just the air getting squished together and pulled apart. And you can kind of see where those waves are getting bunched up. And it's a little bit easier when you highlight it like this. And the other thing that you'll notice is as you get farther away from the speaker, the sound waves get less intense. And that's why it gets quieter. So a wave is a vibration or a disturbance in space that carries energy as opposed to an object carrying energy. So the wave doesn't actually move material from one place to another. All it does is move energy. And so whatever it is that the wave is going through basically stays in exactly one spot, or it moves forwards and back or up and down, but it'll end up back where it started from. But the energy gets transferred from one place to another. And a medium is what the wave is going through. All mechanical waves need a medium to travel. And sound, for example, is going to travel through air. So air would be the medium. So what causes a wave? It'll be a vibration, a disturbance. You need work done because you remember that work is your change in energy. And so you have to do work to make that energy move from one place to another. A pulse is just a single vibration. A wave is going to be a periodic, repeating, continuous series of pulses. Um, Waves carry energy, but they are not going to carry mass. And a medium is going to be the material that the wave travels through. When we talk about parts of a wave, the equilibrium point is going to be the middle of the wave, or I like to think of it as the x-axis. Usually it is shown as the x-axis. The crest is going to be the top of the wave, and the trough is the bottom of the wave. So the crest, I think the crest of a hill. Trough, I think of like if you're going to give water to horses, you put it in a water trough. And so that's the bottom. The amplitude is always measured from the middle of the wave to the top or the middle to the bottom. And they always are the same because otherwise you would not be measuring from the middle. And so just remember that that is that amplitude. So it's not from the top to the bottom, it's from the middle to the top or middle to the bottom. And then the wavelength is just how long the wave is. So you measure that from crest to crest, or you can measure it from trough to trough, either way. Now, this usually makes sense when we're talking about a longitudinal wave. You would measure from the compressed part to the compressed part, or from the rarefaction, which is basically the stretched out bit of the air, to the stretched out bit of the air. And those are rarefactions. So now we're going to draw a transverse wave. A periodic wave has an amplitude of 2 meters and a wavelength of 8 meters, and I want to graph 2 cycles. I can start wherever I want. So I'm going to start at a amplitude of 2 meters. So I'm going to go ahead and draw a dot there. That's where I want to start. And because the wavelength is 8 meters, I know at 8 meters I need to be back at the crest again. And then another 8 meters later, I need to be back at my crest again. Okay, now if my crests are every 8 meters, then my trough needs to be halfway between that. So I'm going to put that at 4 and 12, which is halfway between those crests. And then it needs to cross the middle point or the equilibrium point halfway between those. And then I just need to draw my line. And it's a sinusoidal curve. And there we are. Not perfect, but you get the idea. So my pizza question is this. I have a pizza. I want to know how many slices are there in this pizza. Well, I count them, and there are 8. And then I could say, well, but how much pizza is there per slice? Well, it's 1/8 of a pizza. Um, this relationship is very similar to the relationship between frequency and period. And the reason I say that is I could talk about this as 8 slices per pizza, or I could talk about it as 1 pizza per 8 slices. And they both have the same information. It's just flipped upside down from one another. So if we look at frequency and period, frequency is the number of waves per unit time with units of 1/seconds. And so frequency is the number of waves per unit time or waves per second. And period is the inverse of that. It is the time per number of waves or measured in waves per second. Or, sorry, measured in seconds per wave. So it's the opposite or the inverse of the other one, which means that if you have frequency, you can find period. And if you can find period, you can know the frequency. Wave speed is going to be how fast the wave pulse travels, and that's just your velocity is equal to frequency times wavelength. Super simple. Um, the medium is what the wave travels through, and that's going to affect the speed of the wave. So if we're talking about ropes or guitar strings or piano strings, those big fat loose strings, the wave is going to move slower through them and result in a lower pitch sound, whereas the really skinny or tight strings are going to give you a shorter wavelength. In other words, it'll give you a higher pitch sound. And if you're trying to figure out exactly what that's going to be, you need to start by finding the linear mass density, which is that mu, and it's mass per unit length. And when you talk about the speed of a wave, that velocity is going to be the force or the tension in the string divided by mu. And this is the same mu for the linear mass density, which is just mass divided by length. And then the speed of sound in air is going to depend on the temperature and the density of the air. And so the speed of sound is going to be based on the medium, first of all. So solids, it goes faster than liquids, and it goes faster in liquids than in gases. In fact, steel, it goes 16 times faster than it does in air, and water goes 4 times faster in water than it travels in air, which is crazy. And then if you're talking about just the speed of sound in air, the warmer it is, the faster it's going to go. So if we're talking about standard temperature and pressure, or if you're not given the velocity of sound in air, just use 343 meters per second. Otherwise, if you need to figure it out at a certain temperature, you can just use the velocity of sound is equal to 331 plus 0.6 times the temperature in degrees Celsius. And then just remember that velocity is still going to be your change in position over change in time. And next, we're going to talk about types of waves.